Thanks everybody for joining for the second part of the joint talk with Lygia. It has this name, Ideas and Constructions in Non-Black Box and Superfast Randomization, which is just a fancy way of saying this is the techniques part. I'm going to share some of the constructions and the technical ideas. I'll focus on three results. These are from a couple of papers with Lygia and from a paper with Lygia and with Ron Rothblum. So first we'll talk about the main result that Lygia started with, which is the non-black box hardness versus randomness framework. It relies on almost all inputs hardness. It is based on a new targeted heating set generator. And while it is the most important result, it's also a result that we talked about quite a lot, and I guess many people in the audience have heard about. So I will survey the construction, both because it's interesting and some people haven't heard about it, and both because we're going to need it later. And also I think Nicholas said he will also need it later. He's somewhere here. There he is. So we're going to rush through this part a bit. Then we're going to talk about derandomizing interactive proofs into argument systems with basically no overhead. This is the part that Lygia ended with, which had as a punchline an argument for sharp sapped that runs in better than ETH time 2 to the epsilon n for every epsilon that's as small as you want. And in the end, we'll finish with what Rahul asked about, which is a new result. It's an upcoming work about uniform hardness versus randomness, and in particular overcoming barriers that have stood for several decades as not too complicated corollaries of our techniques. All right, so let's begin. This is the context of what we're going to show right now. For black box derandomization or universal derandomization, we've known for a long time that it's essentially equivalent to circuit lower bounds. And for average case derandomization, we know more or less up to a lot of problems that I'll talk about later, that it's sort of equivalent to lower bounds for algorithms. And in the middle, we have the notion that we care about, which is standard worst case derandomization, BPP equals P. It's always the promised version when I fail to mention it. And we're trying to understand which types of hardness assumptions are sufficient and necessary for that. What is derandomization? What is it equivalent to? Where does it sit in our complexity length map? And this is the result that Lygia presented. So there are two directions, the easy one and the interesting one. The easy one is that if we have derandomization, that then there is a function with multiple output bits. For simplicity, it will be length preserving, but it really doesn't matter as long as it's super constant. And this function is computable in deterministic polytime. But every probabilistic algorithm running in time n to the 100, Lygia wrote 10. I hope we can do 10. Maybe let's say that we can do 10. There is a universal constant there, and it's not big. It's closer to 10 than to 100, for sure. If it's hard on almost all inputs, in the sense that every probabilistic algorithm running in this time fails on 100% of inputs, starting from some length forward, that's the conclusion. There exists such a function. The other direction is that if there exists such a function that's hard on 100% of inputs for fixed probabilistic polytime, and this function is computable in fixed polynomial depth, say n squared, then we have that promise BPP equals promise P. And let's prove it. And to show that promise BP equals promise P, classical results, it suffices to show randomization with one-sided error, so we're just going to show that promise RP equals promise P. And here's the standard complete problem. We're given a description of a Boolean circuit. We want to distinguish between the case that it accepts most of its inputs and the case that it rejects all of its inputs. All right, we're going to do this using a targeted heating set generator. This is the new part. There won't be any PRG here. It's targeted. And here is the targeted heating set generator. So we have on our left our input. The input is the description of the Boolean circuit C. And we have an assumption that there is a function that's hard on each and every input. In particular, it's hard on C. It's hard on 100% of inputs. So we're just going to compute it, obviously. But we're not just storing the outcome. We are storing the computational history when we evaluate this function. So we said that this function can be computed by circuits of fixed polynomial depth, say depth n squared. We run this circuit to compute the function, and we write down the gate values of this circuit. And we think of it as a sequence of rows. We have n squared rows, and each row is of large polynomial width, n to the million. Okay, I don't know. This is a large polynomial. And in the bottom row, we have the input gates, right? So this is the description of C. We'd say pad it by zeros just so we have a nice matrix over here. And in the top row, we have the output, f of C, because this is how a circuit works. And in the middle, we have a bunch of gate values. And this circuit already comes bundled with a structure, because every circuit has structure. Without loss of generality, the circuit is only comprised of NAND gates, and they're of fan-in 2. So this circuit has kind of a downward self-reducibility structure embedded inside. If we look, say, only at the second row, and you tell me, okay, look at the ith entry, I can compute it very quickly if you give me oracle access to the first row. Why? Well, because the ith entry in the second row is a function of two values in the first row, and since we assume there's sufficiently strong uniformity condition on the circuit, we know which places those are very quickly. Okay, this is our starting point. Yeah.
Yeah, I'm sorry. So the notation C1 through Cn, what do we?
So our input is a circuit C.
How does that relate to C? Or?
The description length of C is n. So C1 up to Cn are the n bits that describe this circuit. Is there a confusing point here? Okay, I didn't specify what the number of inputs to this circuit is. I think of it as a linear sized circuit without loss of generality. Right. Any other questions?
I guess you said this, like each bit there depends on only 2 bits below, below, but why is that?
Well, it's a circuit, so it has fan-in 2.
Yes, but that only means it depends on 2 gates. But if you're looking at the representations of the gates, that's probably like log n or something, right? I mean, how do you?
Oh, so what I'm claiming is that if I have oracle access to the function whose truth table is the I-1th row, I can compute each entry in the ith row very quickly.
Yes, you can.
Because I just queried that oracle.
Yeah, but why is it only 2 queries? It's in general more, right?
I'm not sure that I'm following. I just want to query the row below in 2 places. These queries might have length that is log t.
Oh, I see. Okay.
But the amount of information I'm getting is just 2 bits of information. Does that answer your question?
But it's okay. I mean, I can discuss.
Okay, I'd love to understand later.
Actually, to extend Rahul's question, what happens if, I don't know, maybe you answered it, but in a circuit, your input can come from a lower level, right?
Without loss of generality, this circuit is layered, and you can enforce this.
So you're kind of replicating all the gates.
Yeah, you're adding dummy gates so that everything is layered nicely.
This should blow up your circuit size in some amount.
But we don't care about constant multiplicative overheads here at all.
You only care about the depths, right?
Even if you the depth will not blow up. The width, I don't care even about the poly n blow up. And I won't even care about like a blow up of the width by a fixed polynomial amount. So it's fine. The argument is not sensitive to this type of stuff. Any other questions? Okay, this is just the values of the circuit, of the gates in the circuit. And it has structure, but not enough structure for us to carry through the argument that we want to do. So we want to enforce more structure on this set of rows, and we'll apply a transformation that comes from the doubly efficient proof system of Goldwasser, Kalai, and Rothblum. It's essentially implicit in their paper. So the first thing that we do is that we encode each row by a low degree extension, just by the Reed-Muller code.
So when you say the value of the gates, you're talking about not the gates of the input C, but of like applying this hard function?
So this is a computational history, right? We have C as an input. We compute F on C. This means that the entire circuit now evaluates to 0 or 1, depending on the value of that gate when you feed C at the inputs.
Okay, thanks.
This is a 0, 1 matrix. It just has this nice structure. Okay, so we encode each row by the Reed-Muller code, just by a low degree extension And the parameters are set up nicely. 1 second, I'll finish this slide and then leave room. The parameters are set up nicely. The field is of polynomial size, so instead of width n to the million, we now have n2 to the million. The degree is roughly linear or fixed small polynomial if you want. And at the bottom, we have an encoding of the string that just has n bits of information, the description of C and a bunch of zeros. And observe that now we have more structure here, because every row is a code word, but we lost the original structure. We totally ruined the downward self-reducibility. Yeah, Ilya, sorry.
Just maybe a stupid question. So just to be clear, those GIs are the gates of F, right?
Those GIs are the gates of the circuit that computes F when evaluated on the input string C.
Good.
For a second now, I'm totally forgetting that C is a circuit. C is just a description of something. Very good. I know that I'm rushing this part of it. Okay, so we got, and we replaced one structure with another. Our goal will be to have both structural properties simultaneously. And I did nothing here but add visual space. So we add a bit of space between each pair of rows. Okay? And between each pair of rows in the circuit, we're adding constantly many additional polynomials. These polynomials, I won't go into detail, but intuitively they correspond to an auxiliary sum check protocol that will allow us to verify the second row from the first row and the third row from the second row and so on and so forth. And let me just re-index everything here. Forget that I added space and added polynomials. Now I just have a new matrix. This matrix is of depth 100 times n squared, because I added constantly many polynomials between each pair of rows. And it has this nice structure. First I'll say the structure, then I'll say another comment. Well, first, every row is a code word in a good code, in the Reed-Muller code by definition. Fantastic. Secondly, we have this downward self-reducibility property by sum check. So for each fixed row, if you give me Oracle access to the row below it, I can compute each entry quickly, say in time n squared. Fixed polynomial time. Most importantly, much smaller than the width, which is n to the 2 million. This is very quick. And the two additional properties is that at the bottom, the first row is easily computable from the input. It's just the low degree extension basically of C. And at the top, we have the value of the function. And this is the structure that we get in this set of rows. And I want to add another comment about what this set of rows is. Because this was one way of describing it, but another way, which is equivalent, is that after this encoding, each row is the prover strategy in a round of the doubly efficient proof system of GKR. So the last row is the last round of the protocol. The first row, the row on top is the first round. So think about it. In the first round, the prover just tells you what the value of the function is, and you don't believe the prover. Then you go through from the top to the bottom until the last round, where the input is sort of revealed, think in sum check. And you, if it's a public coin, then you look at the input in the end, and you do your verification. Okay, so this was a, yeah.
Why does property 1 hold for the rows you add in between?
Oh, there are polynomials by definition. There are polynomials from the sum check protocol. Setting the parameters correctly, they're good enough codes. Yeah.
Maybe it's not relevant, but could you say what a doubly efficient proof system is? Or
Yeah, sure. It's like totally tangential, but super cool, so we might as well know it. A doubly efficient proof system is a proof system in which the prover is efficient and the verifier is super efficient. For example, it's a proof system for a claim in P, and the prover runs in P, but the verifier runs in linear time, or quasi-linear time.
I see.
It's a super cool notion. Here, this is based on exactly this type of proof system. Just for the proof system is for functions that are computable by log space uniform circuits of bounded depth, which is exactly what you get.
Okay, thanks.
Sure. So remember, this is an algorithm. We are doing it. We are in a targeted heating set generator. I just described a bunch of properties, but the targeted heating set generator got the input C and computed the function f, stored the computational history, encoded it in some ways, got a bunch of rows. Now it thinks of each row intuitively as the truth table of a hard function. We're not claiming that it's hard, but we're going to apply to each individual row the classical transformations that you know, Nissan-Wigderson style. The Adamard encoding, combinatorial designs, the usual transformations of truth tables into pseudo-random sets. So now on the right-hand side, we have a bunch of sets, each set corresponding to the row from which it was produced. And the final targeted hitting set generator outputs the union of everything on the right. We started from C, we computed f of C, we did a bunch of encodings, we applied Nissan-Wigderson type of stuff to each row individually, we took the union. This is a description of the algorithm. Questions about how this algorithm works? Forget about why it's correct.
So, sorry.
Yes.
So
No.
at the most basic level, you're treating each row as a truth table and say, forget everything that isn't just super basic Nissan-Wigderson. Each row now corresponds to a new little row over there. Each little row over there corresponds to a seed.
Each little row on the right corresponds to a big row in the middle and to a seed.
Good, got it. All right.
So think of taking each row, enumerating over the seed, the seeds, it gives you a bunch of little rows. Do this for each big row, you get a bunch of sets of little rows and take the union.
Okay, I'm with you. So each row over here maps to a pseudorandom function family on the right, indexed by seeds for the individual constructions.
You can look at it like that.
Okay. Thank you.
We're not claiming that it's a pseudo-random function, of course, but you can look at it like that.
You could call it an attempted pseudorandom function. Yeah.
Well, we're not. It's not necessarily strongly explicit. We're not bounding the complexity of outputting individual bit in the little row.
Okay.
Good.
Yes.
Any other questions? All right. Why does it work? Well, we're going to apply a non-black box version of the usual reconstruction type arguments. If there is a distinguisher, then there is someone that computes the hard function. The new part here is that both players get this fixed C. This entire game is carried out with respect to this fixed string C. So why is this true? The targeted hitting set generator outputs this thing on the right, I'm going to call it R sub C, as a function of C. And the reconstruction tries to compute the hard function at the same C that it manages to distinguish. And if we are able to do this in time n to the 100, then we win. Why? Well, whenever the function is hard, there is no, for each C for which the function is hard, there is no distinguisher. Otherwise, we could have computed the hard function. So for each such C, the derandomization works. I'm going to get back to this point in the end. Let's see the algorithm. This is the reconstruction algorithm that, assuming that C is a distinguisher, manages to compute the hard function. And if you know if you have in your heads the classical Impaliazzo-Wigderson stuff from the late 90s, this is very similar, just non-black box. So we're going to quickly construct compressed versions of each row in this set of rows from bottom to top. And as an alternative view, we quickly reconstruct the prover strategy functions in the doubly efficient proof systems, starting from the end and working our way back. And how do we do this? Well, the base case is trivial. It's easy, unconditionally. The base case is a low-degree extension of C. We can do this by ourselves. It has no information other than n bits. So we just construct a circuit. And for the inductive step, it's the same old idea. We have a circuit for the first row, and we have a distinguisher for the second row. And we want a small circuit for the second row. Why do we have a distinguisher for the second row? Well, we are doing derandomization with one-sided error. So the circuit avoided all of R sub C. It is 0 on the entire pseudo-random set. And in particular, it is 0 on the second subset. The classical reconstruction argument prints a small circuit for the second row using a distinguisher, which we have, and using query access to the second row, which we don't have, but we have downward self-reducibility and the circuit for the first row. That's it. Overall, we use C that's in our hands to jumpstart the entire reconstruction argument, to compute the bottom row. We can't start without having this fixed C in our hands. Each step takes fixed polynomial time. After running in fixed polynomial time, say n to the 10 times the depth, we're done. And this is much smaller than n to the 100. Yeah?
Can you go back a few slides to the statement of what you just proved?
Yeah.
Okay. What is capital A here?
Oh yeah, my bad, it's just a typo. A is the algorithm. So there's a probabilistic algorithm A running in time n to the 100 such that for any fixed C, if R sub C on the right is not a heating set for C, then when you give A this C, it manages to compute f of C. So A gets as input every C that breaks the targeted heating set generator and manages to compute the hard function at that C. And this brings me right to the slide where I was, because this is just repeating the message. This is very good. The targeted generator comes with an instance-wise guarantee. Whenever A fails at C, the derandomization succeeds at C. So if F is hard on 100% of inputs, the derandomization succeeds on 100% of inputs. If the derandomization, if F is hard on 99% of inputs, fine. We get derandomization on 99% of inputs. And they'd be the same inputs, instance by instance. Yeah, yeah.
Sorry, just when you said inputs are the C.
The C. Yeah. The input now is the circuit C.
Second question, maybe you're going to come back to this. Where exactly did you use Red Muller? Or you just use it for
So the encoding here that uses encodes each row in a code. I haven't specified Red Muller yet, right? I just said a code, and then allows you to do downward self-reducibility between rows, add sum check stuff. We only know how to add this sum check stuff that does downward self-reducibility with polynomials.
Oh, okay. So basically, you don't need Red Muller per se. You need this reconstruction for this the down self-reducibility functionality, basically, right?
Yeah. We just need something that supports this analogous of classical stuff, random self-reducibility and downward self-reducibility. Just that I only know how to do it with polynomials. I asked a guy welcome at some point if he knows how to do GKR without polynomials. He said also no. So it's a good question.
And just to follow up on that, so I guess this is for this construction, but basically, more generally, will it allow you to extend any existing computation? I'm just trying to say you're not using any particular property of this G. Will this allow you to extend any existing computation with those endowed with those two properties of downward self-reducibility and random self-reducibility?
Definitely, but it will not be helpful for us for this particular argument if the depth isn't bounded. Because we call the reconstruction argument, you want it to work fast. Mm-hmm. And the reconstruction argument does a fixed polynomial time computation per each row. The fact that the number of rows is small allows you to get the contradiction again.
But okay, but you cannot. Okay, you want this to be smaller than this, right?
Yeah.
But if this is if this is a fixed polynomial, you cannot work around this. Like if this is not n squared, if this was n to the k.
Yeah, we can do it for every fixed polynomial. 2 is just for simplicity, but you have to increase the 100 proportionally. Yeah.
How does this AAI hardness assumption come in as opposed to other hardness assumptions?
Whatever hardness assumption you stick in, this is the derandomization that you picked.
Oh.
This is an instance-wise guarantee. Super important. If A fails at 99% of the inputs, the generator succeeds at 99% of the inputs, and those are the same inputs individually. We're going to use this in a while. Okay, I'm going to mention 2 extensions of this, because we claim all the time that this is a framework, it's not just a result. Because it scales all around, and whenever you scale it to some direction, the gap between the necessary hypothesis and the sufficient one decreases. It's actually a good framework. So for example, scaling this to the low end, if there is a function computable in time 2 to the n to the 100, fixed exponential time, that's almost all inputs hard for probabilistic polytime, then you have this slightly non-trivial derandomization of RP.
Why do you say IOA?
Yeah, I'm trying to hide this. Infinitely often, 100% of inputs.
Yeah,
But
but
it's true even without the IO, but it's tighter with the IO.
that's why.
Well,
Okay.
ignore it, it's AI hard. With
Oh,
the
is
IO
it because you only will get IO summation anyway? Whether, oh, I see.
Exactly. For the IO, we're almost able to get the converse. Really almost. Give me a second. Okay. So if there's a function that's AI hard, but that function is computable in exponential time, right? Then RP can be derandomized in fixed exponential time. This is non-trivial derandomization. RP in 2 to the n to the 100 is non-trivial. And it's the proof idea here is simple. It's just what we did. It's just a win-win. If E has polynomial size, if E doesn't have polynomial size circuits, we win. Right? Classical results. This is circuit lower bounds, just by a PRG. If E does have exponential polynomial size circuits, well, then E collapses to MA. In particular, the hard function is computable in MA. In particular, the hard function can now be computable by circuits of bounded depth, because you can brute force in MA. And you just throw in the targeted generator at it, and that's it. So, but really, the punchline here is that when we scale this thing to the low end, there is no more condition on the bounded depth. It's almost an equivalence where the only thing is that we randomize promise RP instead of promise BTP. And I wanted to mention something else, but I will say it in like 3 seconds. This also scales to weak circuit classes, down to NC, essentially, or to log space uniform NC. And again, in NC, the gap is smaller than necessary and sufficient. And I plan to spend 10 minutes on this, and I thought that I will exceed to like around 15, and now it's 25, so we're on schedule. But any other questions, nevertheless? Yeah, Roei.
So, I mean, I guess ideally you'd want to remove this like depth restriction
Yep.
on the. So, if you could remove the depth restriction, does that imply anything about proof systems or?
Yeah, not necessarily, because I don't know how you remove it. I didn't see a way. Did you say that you know this answer? Because I heard you answering Roei.
Oh, I just say it depends on how you do it.
Yeah, exactly. Certainly, provably, with our particular techniques, it just captures the GKR proof system.
Okay.
But this is really our particular techniques, obviously. We would have pushed it further if we knew how.
And if I recall correctly, you think that the depth.
Sorry, I continue?
If I recall correctly, you think the depth restriction is removable, probably.
I hope so, and like in an ideal world, it would be possible because it would cleanly solve other problems that we'll talk about later. It seems like a nice, clean, ideal form that solves a lot of problems. Right. Moving on, randomization of proof systems by arguments. So now in our heads, what we have is the following. We have a verifier, which is efficient, say polytime. We have a prover, which is all-powerful, but maybe evil. And we have a common input x that both sides get. And we're going to care about fine-grained time-bound, so let's just define it once properly. So a language is in AM times C with time t, so it's C messages and time-bound t. The verifier runs in time t. It's public coins, so it just sends fresh public coins in each round. The usual completeness, you can prove any correct claim, and the soundness condition that you know of. For every incorrect claim and every evil prover, with high probability, the verifier catches the cheating prover. And the number of messages exchanged between both sides is C. And throughout this talk, C is a constant. And classical results tells us that when C is a constant, then AM with constantly many rounds collapses back to AM with some time overhead. And also, assuming that E is hard for non-deterministic circuits of exponential size, AM equals NP. So basically, AM with constantly many rounds under sufficiently strong conjectures is just NP. You can simulate it by a deterministic verifier. And Lydia mentioned one result that I won't focus on, but again, for context, under hypotheses that I don't have time to cover, so let's hide them. Aha. Okay, magic. Under reasonable hypotheses, I will gladly go over them later. We can even relax what's written here quite considerably. You can derandomize AM with C messages in time t to the c over 2 with some overhead of the input length n. And this is tight, assuming an assumption from the exponential time family. So basically, if you have C messages, you need to pay time polynomial overhead C over 2. And this is unavoidable. Okay, we do want to avoid it, even though it's unavoidable, so we introduce a new notion. And this is something surprising. It's a free lunch, or at the very least, it's a lunch that looks free to any efficient observer. So we define this notion of deterministic effective argument systems, which is deterministic NPtype verifiers, the usual NPtype verifiers that are only computationally sound. So it's a deterministic argument system. So V runs in time t. You can prove any correct claim to V, but any evil prover cannot find a false claim and a proof that will mislead the verifier, except with negligible probability. It's possible to cheat. An all-powerful prover can find bad claims and bad proofs that will convince the verifier, mislead it. But it's infeasible to do so. And okay, as Lee just said, one special case of this would be solving sharp-sat very quickly by an argument system in time 2 to the epsilon n, where epsilon can be as small as you want. I'll mention this later. For now, what I want to do is to carefully define the hypothesis that we need for it, state the theorem, and show the proof ideas. So this is informal. It's the form of hypothesis. Lee already mentioned something of this. Think of a k-wise direct product for a second. So you have a function from n bits to k bits, and you can compute each individual output bit in time t. For example, if it's a direct product, then the original function was computable in time t, so you can compute each output bit in time t. And the hardness is that it's essentially hard to print the entire string in time slightly larger than t. Our usual direct product theorems tells us that k-wise direct products are much harder in terms of average case lower bounds, or in terms of printing even corrupt versions of the original string. But they work via reductions, so the running time never increases. But we expect that for some functions it will increase. And here, for some functions, conceivably, it may increase to time t times k. We have to compute the original function on each individual bit independently. Here we're requiring a mild increase to k to the alpha for some tiny constant alpha. And you can generalize this from direct product functions to any function that has this structure. You can compute each individual bit quickly, but you cannot batch compute the entire thing in time that's very close to just computing one bit. You have to spend more time if you want to print the entire string. Okay. And this is the n to the k, n maps to k, alpha beta non-batch computability for an algorithm class A with time t. It's essentially the same thing, just a bit careful in saying one thing that is new. So again, the function is from n bits to k bits. Each individual output bit is computable in time t, and even in non-deterministic unambiguous time t, like n pick up co-np time t. And the hardness condition is just what we saw before with these new additions. So for every algorithm from the class that runs in time slightly larger than t, and every efficiently sampleable distribution over the inputs, with high probability over a choice of input, A won't succeed in printing a version of f that has that doesn't have this 1% corruption. So the two new things to note is that, okay, first, earlier, and in standard unconditional direct product results, hardness holds on average over 99% of inputs. And in the unconditional results, hardness holds also with respect to this beta. You cannot even print a slightly corrupt version of f. Like you would be wrong on 1% of the output bits. But here the new thing is that this holds not over the uniform distribution, but over every efficiently samplable distribution. We're not there yet. But the next slide is the actual hypothesis. The thing is that I haven't specified what A is. This is the hypothesis. Fix C, a number of terms, fix a polynomial running time, and fix a number, this is a warm-up. So a number of random coins that is subpolynomial, n to the little o of 1. We're thinking of de-randomizing AM protocols that use few coins. Assume that this non-batch computability holds, where the class that struggles to compute the function is algorithms with Oracle access to AM protocols. It is a strong class and it is a very strong assumption. This kind of direct product phenomenon holds when the weaker class is a class of algorithms with Oracle access to AM. And I won't go into the parameters in depth, I will mention them, they make sense. The function is over roughly t bits, and it outputs k, which is n to the little o of 1 bits, and its hardness is with respect to the fixed running time t times k. It's not crucial. If you walk out through the proof, this is the correct value. Then we can de-randomize AM into arguments without paying for it at all. So really what we have here is a hypothesis that makes sense in a generic version. It's a very plausible hypothesis that's taken to an extreme. Since the class of algorithms is the class of algorithms with Oracle access to AM protocols, and an exceptionally strong conclusion. The conclusion is that even if the number of rounds is 1,000,000, we don't pay for it. The running time remains the same when you de-randomize into argument systems. So think of the following intuitive thing to do. This is the thing you want to immediately do. Take a problem, speed up its computation using 1,000,000 rounds of interaction. Now do this. What we're saying is, yes, this is what you do. This is the sharp set algorithm.
So, what evidence is there for the hypothesis itself? I mean, is it true with respect to random oracle, for example?
Oh, I have no idea. If it's true with respect to random oracle?
Yeah, because just to get some sense of whether, I mean, it might just be false.
Yeah, it might be false. The evidence that I can provide. First, for direct product, I'm willing to bet that it's true. Okay? It's probably true. And secondly, if you do superfast randomization for certain very limited classes, for example, balanced formula, stuff like that, you can show that it's necessary. It might be false, but it's necessary.
And how about if you're not so interested in superfast randomization, but just in de-randomizing AM into an arg? What's the weakest assumption you can get away with?
I haven't thought about it, and it's a great question.
Because, it's weaker than...
Yeah. Fantastic question, thank you. I mean, you're saying maybe we can do it with hypotheses that are weaker than like circuit row bounds from other communities. Fantastic. Great. I got the question.
Roei, what was the question?
Classically you can de-randomize MA into NP assuming strong circuit row bounds. Can you de-randomize AM into argument system assuming something weaker? Very good question. Okay, so again, a strong hypothesis and an exceptionally strong conclusion. Let's do the proof of this thing. You know what, let's jump to the special case of sharp set. Now let's do the proof. Okay, this is the proof. And it's a non-black box randomization again. And our building block is a simple reconstructive targeted generator, which is generally an application of Nissan-Wigderson, just a bit careful. So this is a basic building block. On the left you have big N bits. We know that a hard function exists. We just compute it. Now we're not storing the computational history, we're just computing the hard function, we get k bits. And think of the parameter choices in the theorem. N is big, k is tiny. K is n to the little of 1. Apply Nissan-Wigderson. I haven't told you which codes I'm applying. I will tell you in a second, but generically apply classical Nissan-Wigderson tools. Get a sequence of poly k strings, each of length r. These are your pseudo-random strings. Simple enough, right? Haven't done anything. Basic building block to keep in our hands. Now, why is it interesting? Well, the classical reconstruction algorithm that we just saw tells us that we can transform a distinguisher into a circuit whose truth table is f of z. Because we applied Nissan-Wigderson to z as a hard truth table, but it needs queries to f of z. Earlier, we answered these queries with downward self-reducibility. Now, we can just answer them, because we have a hypothesis that individual bits can be computed efficiently, just as in a direct product function. This is the idea. This is why the building block is interesting. And it's useful because of additional reasons. It's super fast. Assuming that r and k are small, this thing is blazing fast, and there's no problem to use it in a super fast setting. And there's one technical caveat, which, as I said, we can't apply an error-correcting code to Z as usual, because it's going to ruin the assumption that individual bits are computable efficiently. So, but we can apply direct product codes and get a circuit that approximates the original string, and this is why we need an approximation. So the basic building block has like a direct product inside of it, but it's not crucial, at least for a high level. Okay, given this building block, what do we want to do? This is the prover, this is the verifier. We have C round, we have C prime, this is C over 2 rounds, C terms of interaction. The verifier sends random coins, or I, it gets answered with an answer, pi I. And the idea is to use the targeted generator in each turn using the transcript as the hard input. Because in each turn, the verifier sees in front of it the information that it gets from the prover is the entire transcript as well as the input. So think of it formally this way. Instead of sending Ri, we choose random coins, random seed for the Nissan-Wigderson generator. We instantiate the Nissan-Wigderson generator with the hard function applied to the transcript so far, and we output the corresponding output string of the generator. I'm going to pause for questions in one sentence. So this is another protocol which has much fewer coins. It has little O of log n coins, because we are still choosing a random seed in each round. And this is where I pause for questions, because I see confused looks. I'll repeat what I said in a different way. The main thing that we do here is we have a targeted generator that works with functions who have this nice structure. And in each round, we want to replace the random coins with a pseudo-random choice of coins. And the information available at that round is the entire transcript, whatever the prover sent, including the input. So this is what we feed into the targeted generator. The targeted generator gets the entire transcript as input. And the main problem, which is not a problem when using an argument system, but it's a generic problem, is that f is easy on some inputs. There exist inputs on which f is not hard. We are not assuming almost all inputs type of hardness here. And the powerful prover can find these inputs and send them. The powerful prover tries to deceive us. And the key observation that makes the proof follows through is that if the prover is efficient, then the transcript at each turn is just sampled from a polynomial time sampleable distribution. Because the prover is the person who samples it, prover along with the verifier, random coins. So whenever you look at a turn, the transcript that you see in front of you, when you average, is just a polynomial, a random variable from an efficiently sampleable distribution. And f is going to be hard with very high probability. So for every fixed prover that tries to find an input and a transcript, with very high probability, the Nissan-Wigderson will give us a pseudo-random output set. Okay, I see a lot of people nodding confirmingly. So it seems to be good, but if there are questions, I'll pause. Good. Now we're basically done, because after reducing the number of coins to be sublogarithmic, we collapse the entire thing to a deterministic verifier, right? The verifier just expects the prover to send all of the possible transcripts and checks for consistency and checks what it would have done on average. And that's it. The analysis turns out to be a bit subtle. I'm going to mention this, but really I'm going to breeze over it quickly. We're going to use a hybrid argument over the terms naturally, because we want to break a single instantiation of the generator. And there's a subtle issue of who is the distinguisher in each hybrid. So assume that this turn over there, the third one is the critical turn in which there's a gap in the probability of acceptance. The distinguisher is everything to the right, the sub-protocol that comes later on. And we want hardness for algorithms with Oracle access to this distinguisher. But the thing is, if you just replace the prover with an efficient prover, then the distinguisher becomes an efficient prover. And this is a broader class of problems, and we lose the hardness assumption. We need a stronger hardness assumption. So, as I said, these are technicalities, and it's a subtle argument. The point is that we need a subtle hybrid argument, which gradually replaces random coins by pseudo-random coins, and an all-powerful prover by an efficient prover in each turn. With some work, it carries through. Yeah, I agree. And as a corollary, before moving to the general case, the sharp sat protocol uses few random coins. The sum-check protocol uses few random coins. So we just need this thing for the sharp sat protocol. So assume that the assumption that I just mentioned, the non-batch computability thing, is true. We get the following sharp sat verifier. There's a verifier that gets an n-bit formula of size 2 to the lil of n, runs in time 2 to the epsilon n, where epsilon can be as small as you want. And for every formula you can make, you have a proof that causes it to output the exact number of satisfying assignments, but no prover running in exponential time, 2 to the O of n, can mislead this verifier, except with probability that it's negligible in 2 to the n. It's needless to say, a small probability. Okay, and indeed the hypothesis is very strong. The conclusion isn't something that we imagined possible before. So either the hypothesis is false or this is true. Both cases are very interesting. And moving to the general case, because this is of course was the easy case with few random coins, we just need an additional hypothesis to reduce the number of random coins in every AM protocol. And this is a hypothesis along the lines of things that Ligia mentioned before. There's a property of truth tables that you can recognize it in time slightly larger than 2 to the n, and is hard for MA protocols, forget about AM protocols with C+1 rounds that have near maximal advice and time complexity 2 to the 0.99. So this is the type of assumption that you saw before. Morally, it's weaker than the assumption that's needed to de-randomize the special case with few random coins, and it allows us to handle the general case. That was it. A pause for questions before I move to the last part. Yeah.
Maybe, I guess, a tangential question which you told me to discuss offline, which I'm fine, but going back to the sum check and the things that you need to do. So, for now, what happens if you know in advance that the number of satisfying assignments is smaller than the maximum? It's like bounded. Does it help you in any way?
You're asking if the complexity of sharp P is different than the complexity of NP or core NP, basically, right?
Not basically the complexity in your scenario, the complexity of Sharpie, but not Sharpie. Sharpie under the assumption that a function can have a bounded number of, like, for example, something extreme, P equals UP or something like that.
I get it, and it's interesting. Let's take it offline. Is that okay? Thanks so much for the question. Any other questions that I can say? Let's take it offline. No, I have time, so if there are questions. Okay, let me remind you that in addition we have a bunch of other results about the randomization of AM and of MA in the standard worst case sense, not into argument systems where you have to pay something in the round. Okay, now we reach the part where like we only briefly touched upon so far. And we are changing context in our heads. So it's a context switch, 10 minutes before the end. Let's do it, we can do it. What we are interested right now is weak assumptions that imply average case randomization. For example, standard complexity theoretic stuff, BPP is different from X, and what can you get from it? And it's a long line of work starting again in the late 90s, and it's analogous. We have these results for non-uniform lower bounds, circuit lower bounds, and PRGs, and we have results here for lower bounds for algorithms and corresponding PRGs that work only on average. And the thing is, I kind of missed it throughout like the first several years of my PhD, that this isn't resolved yet. It started in the late 90s and it's not done. We don't know how to scale these results to the high end. There is no equivalence here. This line of work is open. So we still haven't resolved uniform hardness versus randomness. And let's see what we know. So the classical result from the late 90s is that if E is hard for BPP, then BPP can be randomized in sub-exponential time on average. I will wave my hands about what on average means, just for simplicity. And the best scaling to a high end prior to the new work is something like this. If linear space, so instead of time 2 to the ON, we now have space O of n, right? We're in a smaller class, so it's a stronger assumption. Is hard for probabilistic time 2 to the n over polylog n, then you get a slightly super polynomial randomization of BPP. Infinity of. You can do it, you can randomize RP, you can randomize BPP with advice, or you can randomize RP without advice. The point is really that it doesn't scale to the maximal hardness, 2 to the epsilon n, and to polynomial time randomization. And also you need hardness in P space, basically, instead of in E.
Yeah, I mean, I guess Travis-Vadan gets you with here with 2 to the n to the epsilon and
Exactly.
quasi-polynomial time, right?
Exactly.
But
Yeah,
the issue is that you use Nisan-Wigderson rather than Impulse-Wigderson in the generator. That's the reason why you pay in terms of the derandomization. Isn't that right?
No,
So-
there isn't. Okay, so first, this is essentially a scaling of Travis-Vadan and Vadan. We worked a couple of years ago, and we worked hard on a low level to just scale Travis and Vadan a bit further. This is it. Why it doesn't scale? This is the next slide. Okay.
Right, do we have this? I think you need to assume TQPF instead of space, linear space.
Well, you are paying in the derandomization time anyway, so you can reduce the TBF.
No, I think if you reduce from linear space to TQPF, you have a product to go up.
No, you reduce to our special TQBF prime that has a nice structure, and you don't pay the quadratic one.
Really? Okay, let's take it offline.
Okay. Because for sure TQBF prime is complete for quasi-linear space. So with padding, it's complete for linear space under linear time reactions.
Okay, let's take it offline.
Let's take it, and like in the next paper, let's state it cleanly. Okay, we're going to do something better now. So as I will ask, why can't we do better? What's the obstacle? So there's a classical barrier, really, which is it stood for 2 decades, and we're going to bypass it now. So the argument works only if you have hardness for nice functions, functions with a specific structure, downward self-reducible and randomly self-reducible. So either you assume this annoying narrow hypothesis for a specific function, or you're going to assume hardness in a class and reduce to this function, but then you pay a reduction over. And furthermore, all of the structural functions that we know, they exist only in P-space, inherently. They cannot exist outside P-space, downward self-reducibility. And they're easy. You don't have hardness 2 to the epsilon n for them. You can unconditionally compute them in time 2 to the O of n. So using this approach, you're stuck in P-space and you cannot get polytime.
Sorry, the computer went back to the little of it? Why is that?
This is 2 to the little of n. Think of TQBF. The representation size is more than n bits. permanent square root, 2 to the square root. Okay, this is the new result. Unstructured uniform hardness versus randomness. Because you start with hardness that doesn't have this structure of DSR and RSR. So this is one instance. We have several instances in the paper, but this is, I think, the most appealing one. Assume that there is a function computable by uniform circuits of exponential size. So this is the analogy of E. This is where we want to be. Size 2 to the O of n. And bounded depth. But the depth is like 2 to the n over a million. In particular, this class is much larger than p-space. P-space is contained in 2 to the, than linear space, sorry. Linear space is contained in size 2 to the O of n and depth n squared. This is a vast relaxation, so probably outside p-space. And is hard for probabilistic algorithms in the running time 2 to the epsilon n. Then you get polynomial time randomization. RP equals P, or BPP is contained in P with a few bits of advice. So again, we don't need the structure for the first time. There is no DSR and RSR here, probably inherently, because it's outside p-space. Any hard function in the class would do. You don't need a nice one, and you're not paying some reduction overheads. Any hard function, if it has the right hardness, you win. And you can start with maximal hardness and get polynomial timed randomization. And of course, it's going to use all the targeted stuff that we saw. So here is the idea. We're going to use the targeted heaping set generator that we started with. In the first result, we used it for almost all inputs hardness. Now we only start with worst case hardness. So it's hard on one input. So if we just apply it, we get the randomization that succeeds on one input and nobody's impressed. Yeah. We're going to apply a worst case to average case reduction, and we're going to get hardness on 99% of the inputs, and then we get the randomization on 99% of the inputs. Sound plan, except that this isn't known. Worst case to average case reductions, for example, linear space against BPP, are not known unless you start with hardness for structured problems or you pay reduction overheads. And this is what we solved. I'm going to state two results. Let's start with this. Just for linear space for simplicity, then we'll state it for the large class. We have an optimal worst case to average case reduction for linear space. And the main thing to do, really, we use standard techniques, but the new thing is an instance checkable problem that is complete for linear space under linear time reductions. We construct an instance checker. And same thing, we construct an instance checker for this class of log space uniform circuits of bounded depth, which again allows us to do worst case to average case reductions. I have about 4 minutes, so I'm going to skip the construction of the instance checker. It basically simulates the GKR verifier with a couple of new refinements. So it needs a couple of more ideas, but in high level it's just reducing to a language where the language reflects the encoding of the circuit that you saw before. And yeah, I'm going to skip the proof of the theorem, because there are a bunch of things here. If you want to get the randomization of BPP with a small number of advice bits, we can take it offline. I just want to state one more result. What we saw so far is the general outline, even if some results deviate from it. So there's another line of work considering fine-grained hardness in P and the randomization of BPP. And it goes back to this type of typically correct randomization with circuit lower bounds in P. And also there is a result from 4 years ago of Marco with Russell and Pagliazzo and Manuel Sabin, which, for example, got the, okay, if for every k click is hard for probabilistic time, k n to the k over 2, slightly larger than that, then BPP equals P on average. And we're able to improve this. So assume that for every constant C, there's a family of low-degree uniform arithmetic formulas of polysize that computes a problem hard for probabilistic time n to the C. Okay? A family of uniform arithmetic formula of degree n squared or n cubed. Low degree here is fixed polynomial degree. Then you get that RP equals P on average. Indeed, we don't get BPP equals P. We only get RP equals P. And just let's instantiate this for 1 second. I want to make sure I have time for the next slide, okay? So I'm going to take additional questions afterward. I want to instantiate this for k-click, just so that we see. K-click is definitely computable by a family of uniform arithmetic formulas of bounded size. That's not a problem. So for k-click, assume that for every c there's a case such that counting k-clicks is hard for time n to the c. I don't know about you, for me this is like an obvious assumption. Like, you can't compute k-click in time n to the 10 when k goes to infinity. Okay, maybe you can.
What if Kolmogorov's conjecture is true?
Okay, maybe. This, let me say it in another way that's a bit more careful. This is one of the weakest assumptions that I know of, one of the most plausible assumptions that I know of to imply the randomization in polynomial time. Okay, so the comparison to what was known before is that before we needed the hardness to grow as k over 2. Here we just need the hardness to be unbounded. But the really interesting thing here is that this is not a result about k-click. This is an unstructured result. Any problem with this hardness can be used. It doesn't have to be DSR and RSR. I'm going to wrap up. Just wrapping up also the two talks, there's a new way to do hardness versus randomness, and new approaches and new ways of thinking using this targeted stuff. And we have lots of constructions in different settings. We generate pseudo randomness from the input instead of using classical PRGs in Pagliazzo-Vickers and stuff. And the hardness versus randomness in this new way is instance-wise. For each fixed input for which you have hardness, you get the randomness. There's a new and natural connection between randomization and almost all inputs lower bounds, which should look obvious after we hammered this instance-wise thing for 2 hours. And we have lots of superfast randomization algorithms. And in particular, this notion of deterministic arguments. Some new directions. First, prove the conjectured equivalence between BPP equals P and almost all inputs hardness for fixed probabilistic time. There's a super cool side challenge here. If you only want to prove this for the low end, I'd be delighted to talk about it. How to efficiently merge targeted PRGs. It sounds obvious that we should know how to do it, but we don't know how to do it. We want other approaches, like Rahul asked before, to get free lunch randomization, other conjectures, maybe relaxed, maybe conjectures that are incomparable, but will strengthen our belief that it's possible, because we'll have several sets of conjectures. And we want to explore this new notion of deterministic effective argument systems. Thank you, Rahul, for already suggesting a follow-up question. Right, because something happens with this notion that's unexpected, the speed up for sharp-sat that we didn't expect. So it's a cool notion to explore. And obviously, again, the last line here is from this morning, so it hasn't been thoroughly thought of yet. A lot of new ground. That's it. Thank you very much.
Okay, more questions for Roei?
There's a question in the chat.
I guess the reason you didn't get BPP, oh, thank you, Hanlin, for a great question. I didn't pay Hanlin. Why did we, like, we have a targeted heating set generator, not a targeted PRG. Now, for the first result, fine, two-sided error randomization reduces to one-sided error randomization. But actually, when you scale up, it's not true anymore. They reduce with a huge overhead. It's a composition overhead. Because this is a...
I think he's asking for the polynomial region, not the...
Yeah, I'm on the way. I agree. Good. So whenever we apply this generator, we do only get one-sided error randomization. In the worst case setting, we can reduce two-sided error to one-sided error. In the average case setting, we don't know how to do that. And that is why we get RP equals P. But the underlying interesting thing here is that we don't know how to merge PRGs. You have a bunch of candidate PRGs. The time that it takes to produce them is larger than the running time of the distinguisher, so you can't use the obvious reduction. You know that one of them is good. I'm giving you more seed. How can you merge them? In the information theoretic setting, we know how to do it. This is a merger from extractor theory. In the non-uniform setting, we know how to do it. It's not published, but it's not hard. You de-randomize XORing, it works. In the uniform setting, we have no idea. If we knew how to do it, we'd solve a bunch of problems. Yeah.
So this goes back to something I guess was talked about in part 1 of the talk, where you have derandomization that is like n times t of n of low, and I guess that's like optimal under sharp n sub or something like that. So is there a natural interpretation for this n?
Yes, I didn't pay Roei either. I have two natural interpretations for this n. One is that if you apply the non-uniform derandomization, the classical Adelman stuff, right? You pay this n. The second one is that there's a natural candidate for a problem that should be easy for time t, but hard for the probabilistic time t and hard for deterministic time n times t. And this is the problem. For me, this is more convincing than sharp n set, because I don't know if sharp n set is true. I give you n descriptions of machines. Descriptions are very small, constant or log n, I don't care. It's a promise problem. Each machine runs in time t on an empty input and outputs either 0 or 1. I want you to decide an approximate majority, whether 2/3 of the machines output 1 or at most 1/3 of them output 1. Clearly, you can do it probabilistically in time t. It seems that in the worst case, deterministically, you'd have to pay time n times t. Of course, I don't know how to prove it. And if you have intuition that says that for some reason it's not true, this example is easy, this is also super interesting. But I think this is the natural example to keep in mind for the interpretation of this n.
So essentially, you want to lift the query lower bound to the Turing machine setting. So
Right.
yeah.
So what about switching the infinitely often? That's under it kind of with uniform hardness random straight or something else we don't know how to do, right?
In which of the...
So in IW98, for example, xp equals BPP, or BPP is infinitely often and sub exp on average. While this instance-wise approach might seem to have possibility of allowing you to switch the IO.
Okay, yeah, that's a good... I don't think that we actually do magic in this kind of sense. Both works, like the IW approach and this new approach, run into the same obstacle of merging PRGs. There you didn't know how to merge PRGs, so you got infinitely often. Here we don't know how to merge the PRGs that are the rows, so we get a hidden section because only one of the rows. It's the same technical obstacle leads to two types of results. Yeah.
Sorry, I was waiting for everyone else. I'm asking too many questions, I think.
No, thank you so much.
Can you go back a few slides? Just a clarification for...
Okay, you have to stop me at some point.
Yes, I will. Stop.
No binary search here.
No, the one that you talk about, I see, hold on, that's the one. So just to clarify, you say arithmetic formulas which are hard for BPP. So can you clarify what it actually means? Because this is a 0-1 algorithm, arithmetic formula gives you a field element, right?
No problem. So the formulas are arithmetic formulas. Okay, for the family you also fix a field. The field grows with the input, say polynomial if you want, right? And in the end you have a field element, right? Fix some easily computable function that translates it to a binary input. Now this defines a Boolean function. The Boolean function can either be easy or hard. But it's not holy. Like if you tinker with our formulation, the result will still hold. This is just the nicest thing.
Well, hard you mean it's not computable. You cannot evaluate the slow degree polynomial in this time, right?
Because the family is of poly size. It's of size n to the million, and you cannot evaluate it in probabilistic time n to the 10. For example, it's the family for k-click, where k is a million. So it's of size like n to the million, right? The brute force, million, whatever, right? N to the million. And I don't know how to do it in n to the 10. It doesn't seem possible.
So it's not just for click, it's for anything, right?
Yeah. K-click is just the example to keep in mind, but the punchline here isn't a quantitative improvement over k-click. The punchline is that any function from this family would do. And we have other subclasses in which hardness would do. It's just a nice example.
Sorry, if I can, I don't know, ask a question. It's like a dramatic relaxation of the structure, right? Like, if you had been able to take this all the way to Boolean circuits,
right,
that would be one thing. But it's like you're saying, the only structure that I need is, it's an arithmetic circuit. and then just from, it's an arithmetic formula,
Of
and then
degree
just-
and squared.
and then just from that you get your worst case to average case reduction of downward. So that's really nice.
Thank you.
It's like saying you can't fiddle with the bits to get it done in n to the c.
What do you mean can't fit in with the bits?
I mean that it's saying, okay, I give you randomized time and I give you a normal RAM where you could manipulate the like bit encoding of the field elements.
Mhm.
Those kinds of tricks will not accelerate computation down
Okay,
to this. That's much nicer than just like the K-cleat conjecture.
Of course, the analogy here is exactly the same as before. Where instead of assuming DSR and RSR, you take a large subclass of the natural place you want to be, and any harnessing it will do without overrides.
Okay, I think we should wind up and have the break now. Let's thank Roei again.
Thank you very much.